Our last topic of the quarter is determinants. We've seen that the inverse to a matrix A that's 2 by 2, so a 2 by 2 matrix, A, B, C, D, exists when AD minus BC is not equal to 0. This quantity here, AD minus BC, this is the determinant of a 2 by 2 matrix. So this is the determinant of a 2 by 2 matrix. So for example, just brief, the determinant, sometimes written DET, and then you put a matrix in here of 1, 2, 3, 4. This is also sometimes denoted with straight bars around the matrix. So if I put straight bars around the matrix instead of having these top and bottom little indicators here, then this also denotes the determinant. So the determinant is the product of 1 and 4. So I multiply those two numbers to get 4. That's A times D. And then I subtract multiplying these two numbers. So minus 6. So 4 minus 6 is negative 2. Now, if you have a larger matrix, here's how to do the calculation. So the determinant of an n by n square matrix, to even do the calculation here, you must have a square matrix. So the determinant of an n by n matrix A is the following. So you could write straight lines to indicate you're taking a determinant. I have an n by n matrix, so let's say the first entry is some number A11. The next entry going across the top row, A12. And I have n columns, so the last entry in the first row I'll denote by A1n. And then I have A21, A22, a bunch of other numbers. Here's how you do the determinant. You look at this top row, and you're going to expand along the top row in the following way. You take the number A11, and you multiply A11 times the determinant of the matrix you would get if you deleted row 1 and column 1. So I'm going to denote that matrix by A11. So A11, in other words, is A with row 1, column 1 deleted. Then I'm going to subtract. I know it's a little bit of a convoluted calculation at first, but I'm going to subtract the next number, A12, times the determinant of the matrix that I create by deleting row 1 and column 2 from the matrix. Then I'm going to add A13, the determinant of the matrix found by deleting row 1 and column 3. And I'm going to keep adding and subtracting until I get to the last number. So A1n, the determinant of A1n. The pattern of the plus and minus signs alternate. So plus, minus, plus, minus, plus, minus. All right, we have to see an example of this process. So let's try the determinant of the 3 by 3 matrix. 0, 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to take this determinant and look at the top row. The top row starts with 0, so I'm going to put 0. Then I'm going to write down the determinant of the matrix you find by deleting row 1 and column 1. So I'm going to erase row 1, I'm going to erase column 1, and I'm going to be finding the matrix 4, 5, 7, 8. So I'll take that determinant in a second. The next entry in the top row is 1. So alternating plus or minus signs, I have a minus sign here. So minus 1 times the determinant, deleting row 1 and column 1. So I have 3, 5, 6, 8. Then I'm going to have plus 2 times the determinant of 3, 4, 6, 7. Then I could just take the determinants because I know how to do the determinant of a 2 by 2. The determinant of this first matrix actually doesn't really matter because I'm going to multiply that entry by 0. So I'm not going to even do that calculation. This next calculation will be 3 times 8, which is 24, minus 30. So this determinant here is negative 6. And then I get 21 minus 24. So this is negative 3. So the answer would be negative 1 times negative 6 plus 2 times negative 3, which would be 6 minus 6. In this case, answer 0. Let's do a couple more examples. What if I took the determinant of negative 1, 2, 1, 2, 1, 0, and 1, 0, 1. Okay, I look at the top row. I'm going to expand along the top row. I get a negative 1 times the determinant, deleting row 1 and column 1, so 1, 0, 0, 1. That's the 2 by 2 identity matrix. Minus, let's see here, 2 times 2, 0, 1, 1. So I delete that row and that column to get 2, 0, 1, 1. Plus 1 times 2, 1, 1, 0. Okay, and then you could just do the calculation. So I get negative 1 times 1, so negative 1. Then I get plus negative 2 times 2, because it's 2 minus 0, plus 1 times negative 1. So I get 0 minus 1. So 2 times, let's see here, negative 1. So I believe I get negative 1, negative 4, negative 6. So the determinant is negative 6. Why don't I do one more brief example with a larger matrix? What if I had a 4 by 4 matrix? So what if I tried 1, 1, 0, 0, 0, 2, 0, 0. I'm trying to put a lot of zeros in here so I can multiply by 0. You'll see why in a second. 1, 2, 3, 0, and 1, 2, 3, 4, let's say. All right, so I expand along the top row. I get 1. 1 times the determinant of the matrix created by deleting that first row and first column. So if I delete that first row and first column, I get the 3 by 3 matrix shown here. Then I subtract, I'm going to alternate plus or minus signs, so subtract 1 times the determinant of the 3 by 3 matrix found by deleting the first row and the first column. So I get 0, 0, 0, 1, 3, 0, 1, 3, 4. Then I get 2 more terms, but I don't feel like I want to write them down because they're going to both be multiplied by 0. So I'm going to get plus 0 times the 3 by 3 determinant, plus, minus 0 times another 3 by 3 determinant, but those are multiplied by 0, so I don't have to worry about them. Now I could take each 3 by 3 determinant doing the process I did in the previous examples. So this can't be a long calculation if you find the determinant using this method. But in this example, I put in a lot of zeros to speed things up. If you notice, this row, the top row, is all zeros in my 3 by 3 matrix. So when I calculate the determinant, I'll have 0 times something plus 0 times something plus 0 times something. So that's just 0. And then I could take the determinant of this one, expanding along the top row. So I get 1 times 2 times the determinant, deleting row 1 and column 1, which would be 3, 0, 3, 4. Again, I have 2 more zeros, so I don't have to write down those terms. And then lastly, taking the determinant of this matrix, I get 1 times 2 times 3 times 4, which is 24. Now, the key fact about determinants, the whole reason we're discussing them in this class, is the following theorem. The inverse matrix exists exactly when the determinant of A is not 0. So if we look back in our examples, this matrix, this 3 by 3 matrix, does not have an inverse matrix. So you cannot find another matrix to multiply with this one to get out the identity. So this has no inverse, but these other two matrices do have an inverse. This should remind you of just regular numbers, because you cannot divide by 0. You cannot have 1 over 0. That doesn't make sense. So if A was just a real number, it couldn't be 0 to have a multiplicative inverse. Analogously, if you have a matrix A, you can't have a multiplicative inverse to the matrix if the determinant is 0. Okay, wonderful.